We are continuing with atomic history. Yesterday we talked about some scientists that helped us understand some things about atomic structure, and we looked at Thomson's model, and we saw that his model was basically the plum pudding model, that there is just this scattering of negative charges, these electrons in there. So that's what we saw with Thomson, and then Rutherford came along and he wanted to prove that the atom was mostly empty space, and what he ended up also proving is that those positives are contained in that tiny, really dense nucleus, and those electrons are outside of that nucleus somewhere. So that's where we left off. Now, don't worry about getting your notes out from yesterday, but at some point you can kind of look over those and see that it continues on with a scientist named Bohr. But this is where we're left off, and we again, this is really repeating what we just said. We know protons, neutrons, and electrons are part of our atom. We know that the electron is negative, the nucleus is positive, so that's what Rutherford helped to explain. So negative charges are attracted to positive charges. We also know that there's an attraction between opposite charges. So now the question becomes, right here, why does the electron stay outside of the nucleus? Why does it not come crashing in towards that positively charged nucleus? And the answer to that came from Bohr, Niels Bohr. And what he did was he proposed that electrons are arranged in concentric circles that rotate or revolve around the nucleus. So he considered these electrons as being in orbits. And these electrons are in a path. I'll move this here. And the path has a fixed amount of energy, and that's a key part of this, is that there is a fixed amount of energy that those paths have. Therefore, those electrons do not lose energy and come crashing in towards that nucleus. So that's what Niels Bohr, contributed. This is known as the planetary model, and you can probably see why that is, because you've got your sun in the middle, and then you've got those electrons like planets orbiting around the sun or the nucleus. Okay, so now, in order to understand some of this, we're in the modern view of the atom, what we're going to need to know about is light, because we're going to see that a lot of those behaviors are the same. So in order for us to think about light, the first thing we need to understand is that light is a wave. And so on your notes, this you have in your notes. It's a slightly different font, but you should see that we've got wavelength, speed, and frequency. So make sure you can identify that in your notes there. Those are the different parts of a wave that we're going to be focusing on. And our first one, wavelength, this is a Greek symbol of lambda. It looks like an upside down, backwards Y. And this is what we use to symbolize wavelength. Just like it sounds, it's a length, so we would expect our units to be in things like meters. And the wavelength is the distance between the peaks of the waves. Another way of phrasing that is that it's between the crests. So for example, right here, from this point to this point, that would be considered a wavelength. You could really also say it's the same thing as between the troughs. So from that point to that point, it would be exactly the same point. Or if we had our nodal line in here, right in between, it would be every other point that hits on that line, that nodal line. So all of those are showing the wavelength. That would be one wavelength that we've represented right there. And again, it is measured in something like meters. We're going to see that another common, because that's pretty long, we're going to see another common unit is nanometers, and we're going to be able to make that conversion pretty easily. Okay, so the second variable that we want to look at is speed, and this is the speed of light that we're talking about, and it's symbolized with a lowercase c. Remember, the speed of light is a constant, so that you might want to think about that being your c. It's a constant. And I have changed this on my notes. I'm not sure if it's changed on yours. Actually, I know it's not. Yours, I believe, says 2.998 times 10 to the 8th meters per second. Let's just go ahead and change it to 3.00. Make it easier. So there is our speed of light that we should have memorized. You should know that. And just like you would think, speed is going to be distance over time, so we would expect our units to be something like meters per second for speed. Okay, then our last variable that we are going to look at is frequency. And the symbol for that, it's the Greek letter that's called nu, and it's really like a V with a tiny little hook on it like that. So that's what a nu symbol looks like. Just be careful, because I have no idea what the state of Texas is going to do when they do the STAR exam, the end of course exam. There is a very good chance, I think on their reference sheets, they use the symbol of an F, but in class we are going to use the nu symbol. So just realize if you were to see that in the formula, that symbolizes frequency. And frequency has to do with the number of waves that pass by in a given amount of time, and that time is typically a second. And so we're thinking about it as cycles per second. So what would you guys think would be units that you would use if all we're saying is the units are per second? How would you write that down? What's one way? Per second, what would you write down? 1 over seconds. There we go. So 1 over seconds is one way that you could write that down. Seconds to the negative first. There's somebody paying attention in math class. Nice. So those two are exactly the same thing. What if you think about listening to your radio and you tune it into a certain frequency? Have you ever looked on your radio dial? What is that frequency measured in? Hertz. So it's spelled like the car company, but the symbol is just H, capital H, lowercase c. All of those are exactly the same thing. On your radio dial, I believe it's megahertz or kilohertz, depending on which station you're talking about. So there we have frequency. Those are the units that we're looking at. So we know these are our three variables. We want to take these three variables and throw them together into a formula. And here is our formula that you are responsible for knowing. So I don't know if you want to put a big bubble around it or star it, something like that. So keep in mind what a formula like this tells us. If we see that we have, you know what, I'm going to go back a second. I was going to say we have this constant, this speed of light. But you know, right here, I think I want to even change this. This is the speed of light, but make yourself a little note that it's actually the speed for all electromagnetic radiation. That'll make more sense in a minute when we talk about electromagnetic radiation. So all electromagnetic radiation travels at that exact same speed. So now when we look at this formula, we have our wavelength times frequency equals our speed of light. If we know that this is a constant, what happens if wavelength goes up? What does your frequency have to do? Go down. So what type of relationship is that considered? Inverse, yay. So they are inversely related, inversely proportional. But it's important to know that if your frequency goes up, your wavelength has to go down, and vice versa. And then you have this diagram on your notes as well, just showing you a picture of what a wave would look like. I'm going to go ahead and flip to this one, which you don't have, but this is just kind of illustrating what we just said about that inverse relationship between those two variables. So in this first example, you can see that we have a low frequency. Let's pretend that this whole entire length of this line, this takes place over 1 second. So in this case, you can look and see, well, from here to here is one wavelength. From here to here is another wavelength. So we have 2.5 waves that pass by in 1 second. So that is a low frequency. Whereas during that same amount of time, from here to here, that 1 second, in the second example, you can see that we have a whole lot more waves that pass by in that 1 second. So you have a much higher frequency. When you have a high frequency, you have a shorter wavelength. When you have a low frequency, you have a longer wavelength. So this is just illustrating that fact that we said that they are inversely proportional. So that should be something that you fully understand. Okay, so now what we want to do, we've learned one formula, and we want to take that and also be able to, at times, combine it with another formula. So we want to be able to think about how there's a relationship with energy. So energy, our symbol for energy is going to be, our variable is just a capital E, and the units that we're going to use are joules, which is just a capital J, and it's spelled like that. It's pronounced just like jewelry, the jewels in jewelry. So the energy carried by a beam of light depends on its frequency. And what we're going to see here, let's think about our relationship between energy and frequency. If I were to change this around, and I'll describe what these things are a little bit better here in a second, but this is a constant, our h is a constant. So if we change this around algebraically, you should be able to see that you get your energy divided by your frequency. So based on that mathematical formula, what does it mean? If energy goes up, in order for this to remain constant, frequency has to go down. Go down. So in order for, wait. Erase that. Zip back. I said that incorrectly. People in the audience said it correctly. So if energy goes up, frequency has to go up as well in order for this to remain constant. So sorry about that. This is a direct relationship. If energy goes down, frequency has to go down also in order for that to remain constant. So this is a direct relationship. I don't know if it says it somewhere here or not. Maybe not. So let's just write ourselves a note that that energy and frequency are directly related. Energy and frequency are directly related. So now we should actually bring up this formula. I kind of jumped around a little bit, but we've got this formula. Energy equals frequency times a constant, and that constant is known as Planck's constant. You do have to know the formula, but I will give you this constant. You can just always look that up. That's not something you have to memorize. And I think that's about all we really want to say about that formula. But what you should note from this is that a common variable in both formulas is, well, where is it? Is frequency. So that one variable is being used in both formulas. So that's going to allow us to be able to relate our energy and our wavelength as well. All right, so now our last paragraph on this page, it brings up the idea of electromagnetic spectrum. So light has a variety of frequencies and wavelengths, and all of these can be represented on an electromagnetic spectrum. So there's a range of frequencies and wavelengths. So I'm just going to go ahead. You guys have room at the very bottom of your page there to jot this down. But the electromagnetic spectrum, if we were to start off with something that has a really high wavelength, not very harmful at all, it would be something like radio and TV waves. Then after that, we have microwaves. And then infrared waves. Then we get the visible light spectrum. Then ultraviolet. After that would be X-rays and gamma rays. And I'll break that apart even more here in a second. But just based on those words that you see up there, which side do you guys think has the most damaging, most high energy radiation? Yes, everybody's pointing over here at gamma rays. So this we would expect to be high energy over on this side, meaning over on our left-hand side, this is going to be low energy. Well, thinking about what we learned here, energy and frequency are directly related. So what this means over here, we have high frequency. Whereas over here on the left, we have a low frequency. And then if we want to then relate it to wavelength, if this is a low frequency on this side, what does that mean in terms of wavelength? High. So we'll say a very long wavelength, whereas this is going to be a short wavelength. Okay, so understanding that relationship is going to be important for you guys. And then we can further break down the visible spectrum into the actual colors that we see, and everybody knows Roy G. Biv. I can't write it, but we know it. Roy G. Biv, there we go. And just like you would think, red has a longer wavelength than violet. It goes in this order because we've got less than red, infrared, then red, orange, yellow, green, blue, indigo, violet, and then greater than violet, ultraviolet. So that's the order that it works in. Okay. You do have a picture also, which looks kind of like that. So it's just describing it again and giving you some rough values for wavelengths and frequencies. We've already said this, but it's worth stating again, especially since I kind of blew one on talking about energy. Relationship of your frequency and wavelength. What do you want to say? Inverse. Inverse relationship. What about wavelength and energy? What is it? Correct. And then here it says that remember that white light is separated into, I can't read, into a continuous spectrum when it passes through a prism is what that says underneath there. So we'll talk about more of that. I think it's tomorrow. And then, oh, quick little cartoon. I know this is really hard to see. I will read it to you guys. Do you sell ultraviolet bull? Excuse me? Well, what about regular violet bull? No. Blue bull? No. Green bull? Yellow bull? Orange bull? No, no, no. Rats. Okay, I'll take a red bull. I was hoping for something a little higher energy. At least it is an infrared bull. Okay, that's funny stuff right there. Okay, and last thing that you might want to jot down on your paper is a definition for a photon. And as we start talking about the relationship between energy and particles, this will make sense to you guys. A photon is a particle of electromagnetic radiation. You can abbreviate EM radiation with no mass that carries a quantum of energy, meaning a very discrete certain amount. So photon is a particle of EM radiation with no mass that carries a quantum of energy. And that now brings us to our 3 practice problems that we're going to work on, so you'll need calculators for this. And as we go through these conversions or these problems, you might want to remember this one conversion that we've talked about already, and I know that you guys have memorized, but here it is again. Maybe an easy way of remembering this is just this part right here, that 1 meter equals 10 to the 9th nanometers. So, first example. Here it says to calculate the wavelength of light if we have a frequency of 4.8 times 10 to the 15th seconds to the -1. And we want to calculate that wavelength in both nanometers and meters. First of all, even if it didn't tell us frequency right here, I'm hoping that you guys could look at that and say, yeah, I'm getting information as frequency. That is telling me the frequency because I can see seconds to the -1 would be describing frequency. So based on this information that we've got wavelength, frequency, the first one I'll just kind of mention. Hopefully you can see that that is the formula you would use. So you've got wavelength times frequency equals your speed of light. Now comes the question, what do? Do we use algebra? Do we use dimensional analysis? And the answer is yes, you can use any of that, I guess. So I'm going to change this around and use algebra, just using these formulas, and I'm going to plug in my units so that they cancel out correctly. So the first thing I want to do is I want to solve this for wavelength. So I know that wavelength is going to equal my speed of light divided by frequency. Now, it gets a little bit confusing. We've always said start with the 1 unit, and this is a little bit more confusing here if you did that because we're talking about something that has the unit in the other, in the denominator, you know, depending upon what, you have to flip it from where the number is. So that makes it a little bit more confusing. So I'm just going to kind of stick with algebra a little bit more, showing the units and how they cancel out. So our speed of light we know is 3.00 times 10 to the 8th. And that's going to be in meters per second. I could do meters / seconds in the numerator, or I could put it in the denominator. There's no reason I can't do it like that. I am going to divide that by my frequency, which is 4.80 times 10 to the 15th seconds to the -1. So what happens when you divide by a fraction? You multiply by the reciprocal. So in other words, that threw my seconds up to the top. If you wanted to have it as meters per second over 1 over seconds, I guess you could do that. There's no reason you couldn't have done it that way. But what I see from this is that my seconds end up canceling and I get my answer in meters. I guess we could go ahead and get an answer at this point. Anybody get an answer? Okay. How many sig figs? Wait. What am I doing? Okay, here we go. 6.25 times 10 to the -8, and that's going to be in meters. What I want us to do is really base our sig figs on that guy, because this is a conversion factor. So, meaning that we'll always be able to at least have 3 sig figs, but this isn't going to limit how many sig figs we have. So I'm basing it on this, happens to be the same. Okay, so there is our number of meters. So now what I can do is just easily take that, and I can get rid of my meters and go to nanometers. So I'm using dimensional analysis to make sure that this conversion works out well. Which one of those is bigger? Meter. So one of these big things, there's 1 times 10 to the 9th of these little things. So now when you plug it in, and remember, if you plug it in, you have to plug in 1 and then second function EE9 is how you plug that in. And so our answer in this case, here it's easier for me to not put it in scientific notation. I'm just going to go ahead and write 62.5 nanometers in that case. Okay. So there is our first problem. Second one. Again, we're given all those little reminders. We're told that lithium exhibits a red light of wavelength 670.8 nanometers when its atoms are excited. We want to figure out what the frequency and the energy is of that light. So, you're given wavelength. Based on that, what's the first thing you need to calculate? Frequency. You have to calculate your frequency first, because we see that frequency is part of both of those equations. So we're going to start with this equation, and we're going to say that we want to calculate our frequency. So that's going to equal speed of light divided by our wavelength. So 3.00, oops, forgot my times 10 to the 8th meters per second. I am going to divide that by my wavelength, which is given to me in nanometers, 670.8 nanometers. Nothing's canceling. So looks like I need to get my meters to cancel, and I need my nanometers to cancel in order for this to work out, because I want my answer as frequency, which we know is 1 over seconds. So I want all of that length to go away. So one of these big things, 1 times 10 to the 9th of these little things. So now you just plug it in, because everything cancels out nice and neatly, and we've got our answer as 1 over seconds. And for the sake of time, I am going to go ahead and be the calculator here. Again, I'm going to look at this, and I'm not going to base my sig figs on the 3.00. Instead, I'm going to base it on this, because this is not a conversion factor. So my number of sig figs is going to be 4 on this, and it becomes 4.469 times 10 to the 14th, and that's going to be as seconds to the -1, 1 over seconds, hertz, however you want to phrase that. Just know that if you use hertz, that's not going to cancel out in scientific notation. You have to convert that. Okay, so now we've got our frequency. We also know Planck's constant, so we can easily solve for our energy. and our energy is going to be equal to Planck's constant, which is 6.626 times 10 to the negative 34th, and that's going to be joules times seconds. And we are going to take that and multiply it times our frequency of 4.469 times 10 to the 14th, 1 over seconds. So notice how seconds is in the denominator now, meaning we will get our answer is joules, which is exactly what we expect. And our answer is 2.961 times 10 to the negative 19th joules. Okay, we have one more problem. And this is really about as tough as they get, where you've got two-step problems, so you just have to think about which step to do first and the direction to go. So here a certain light has an energy of 4.86 times 10 to the negative 20th joule. So we're given energy, we want to figure out our wavelength. This is what we're given, this is what we want to figure out. So we're going to have to think about frequency, solving for frequency. So the first thing we're going to do is we're going to take this formula and we are going to solve for our frequency. So it's going to be our energy divided by Planck's constant. So we're going to take our 4.86 times 10 to the negative 20th, that's in joules, and we are going to divide that by Planck's constant, which is 6.626 times 10 to the negative 34th, joules times seconds. Joules go away. I'm left with 1 over seconds. Yep, that's what I want for frequency. Plug it into my calculator, and I know I'm kind of going through this kind of quickly, but make sure you guys are not making the mistake of how you plug in these scientific notation values into your calculator. Make sure you can get it to the right number for your exponent. And when you plug this in, you will get 7.33, I'm looking right there, times 10 to the 13th, and that's going to be in seconds to the negative 1. So our very last step, because what we want to do is find that wavelength. So our last step, once you've got that frequency, you can plug it into this equation up here and you can solve for your wavelength. Wavelength is going to be speed of light divided by frequency. So 3.00 times 10 to the 8th meters per second divided by my frequency of 7.33 times 10 to the 13th, and that's in 1 over seconds, so my seconds really flipped up there. Seconds cancel. I get it as length, which is exactly what I wanted. Get it in meters, so I can feel pretty happy about knowing I set it up correctly. And then I'm going to round this to 3 sig figs, which is 4.09 times 10 to the negative 6th, and that's meters. It didn't ask for the nanometers, so I would just keep it as meters in that case. Okay, hopefully that made sense to everybody, and there is homework that goes along with this as well.